Imagine a bird call. You hear it, but is it a house finch? Or a similar sounding species? In bioacoustics, we don't just rely on sound. We also use location, time of year, and ecological patterns to guess the species. But here's the problem: context isn't always reliable. A model might be confident in a location, but wrong. And audio models, they can be fooled by similar calls. So what if you could dynamically decide when to trust context and when to stick with audio? Enter FINCH, fusion under independent conditional hypotheses. It's a smart, adaptive way to combine two predictors, a powerful audio classifier and a spatiotemporal prior, like eBird data. Instead of using fixed weights, FINCH learns a per sample gate, a tiny neural network that looks at uncertainty, confidence, and context. It asks, is this context actually helpful here? If the audio model is unsure and the location says this species is common here, FINCH boosts the context. But if the prior is vague or the audio is confident, it ignores it. The result? A fused prediction that's more robust, more accurate, and never forced to trust bad context. Crucially, the audio-only model is always recoverable when the gate hits 0. No risk of overfitting to flawed data. On benchmarks like CBI and BirdSet, FINCH beats both audio-only models and fixed-weight fusion, even when context is weak. It doesn't need joint training. It doesn't need retraining. It just adapts. This isn't just for birds. It's a general framework for any time you have multiple heterogeneous sources of evidence: medical diagnostics, climate modeling, robotics. When evidence varies in reliability, adaptive fusion wins. FINCH proves that safety, accuracy, and modularity aren't mutually exclusive. And in the real world, where data is messy, that's what matters. The future of fusion. Not fixed weights. Not full joint models. But smart, bounded, adaptive reasoning.